Welcome to lecture number 2 for ECE476 Advanced Embedded Systems. In this lecture, we're looking at the Thonny operating system, the Thonny programmer, and the program window. Now, again, this is the second course or second lecture of a course offered at North Dakota State University called Embedded Systems. If you're trying to follow along, just go to Bison Academy down here at the bottom under 476, the other courses we offer. 476, this is the course. The lecture notes are all over here. The YouTube recordings will appear here shortly. They're not there yet. Along with sample code. This is lecture number 2. You can click on that. That'll bring up these slides. Again, this is the second lecture out of 35 different lectures for Advanced Embedded. What we're looking at on this one is how to write programs using MicroPython and the Thonny programming language, using the Thonny shell. So kind of a background. The Raspberry Pi Pico is a microcontroller version of the Raspberry Pi. It can be programmed in assembly, C, Python, other languages. In this course, we're focusing on MicroPython. That's a subset of Python designed for microcontrollers. Basically, it's a stripped-down version. There's not a lot of memory on the Raspberry Pi Pico, so they stripped it down to just the bare minimum, so you actually have room for your program. To get Thonny on your computer, all you really need to do is just do search for Thonny, and it'll bring up thonny.org. With this, I can download the Thonny programmer for Windows, Mac, Linux, your favorite. What that looks like, if I start up Thonny, here's what Thonny looks like. Get it moved around so you can see it. Currently, if I go to the lower right corner, well, what the different shells are, this is your program window. This is the shell. It's kind of like the command window in MATLAB. And here is where you connect to your Raspberry Pi Pico. Currently, nothing's connected. If I take my Raspberry Pi Pico, this is one from Adafruit, plug it in somewhere. Plug it in. There's a little beep. Said I just saw that. Click on this again, and it tells me this is the Raspberry Pi I'm going to connect to. Now, first time you connect, it's going to ask if you want to download the Thonny operating system or Raspberry Pi Pico. Click yes. The one I'm using is the Raspberry Pi Pico-W. That'll take about 10-15 seconds. Download the code you need to run Python. Once you have that, I can now click, and I'm connected to my board. Now I've got two different windows up here. And the top one, kind of ignore for now. This is the command window. From here, I can run Python programs. So again, to install Thonny, find it on the web, install it, select your pick, basically click on the lower right-hand corner. Once you do that, you're going to get a couple different windows showing up. The Thonny command window is the one in the lower right corner. This looks very much like the MATLAB command window. For example, over here, I can type in something like, what is 2 plus 3? And it says the answer of 2 plus 3 is 5. I can have variables. A equals 2, A equals 2, B equals 3, C is A plus B, and C is 5. So again, it looks very much like MATLAB. I can assign a couple of variables all at once. I can say X, Y, Z is 1, 2, 3. Gives me 3 variables. And like MATLAB, Python is an interpretive language. What that means is as you write your program, it calculates or executes it line by line, and it can see the result of each command. What's nice about that is you can sit there and check your results. If you made a mistake, fix it, then go on to the next line of code. So that's very convenient to use as an interpretive language. It comes at a cost though. Python is slower than C. Typically Python, well, every time you go up a level, you increase the code size by 3 to 10 times, decrease the speed by 3 to 10 times. So C is about 3 to 10 times slower than assembly. Python is 3 to 10 times slower than C. But the advantage is you wind up with a language which is much easier to use, easier to modify, easier to build upon. For example, spring break in 2024, I have never used Python before and just got one of these development boards. Within a week, I was writing code to drive the graphics display. That's actually pretty impressive. Python is a very, very friendly language. If you want to know which language is best, well, it really depends. If you really need size, small size, need speed and power, use assembly. Assembly is going to be faster than C, much, much faster than Python, but it is really hard to debug, really hard to modify. Assembly is what I call throwaway code. If you have an assembly program and you need to modify it, it's almost easier to throw it out and start over. If you want code which is reusable, but you still need speed and number crunching abilities, that's where C kind of shines. C is a whole lot easier to use than assembly. It compiles, it's fast, it's a little bit slower, it's larger than assembly, but C is just a great number cruncher. If, however, you want to incorporate features such as a graphics display, touchscreens, web interfaces, stuff like that, that's where Python shines. That's what this course is all about. So we're going to be using Python and doing things like accessing a graphics display, touchscreens, web interfaces, and so on. So in short, programming languages are really just tools. If the tool helps you do your job, use it. If it doesn't help you do your job, don't use it. It's kind of up to you. So anyway, back with Python. In Thonny, you've got the command window. That's in what MATLAB would call the command window. In the command window, you can type in operations. So again, I can do things like this. Okay, where's Thonny? I can go over here and type in, make the cell smaller so we can see what's going on. I need space. There. If I hit stop, that clears out the old program, get a new one. I can say what is 3 plus 5. 3 plus 5, if I type it correctly, answer is 8. What is 2 plus 3 times 7 plus 8? 75. I can put resistors in parallel. What is 1 over 1/50th plus 1/60th plus 1/70th? So if I have 50 ohms in parallel with 60 ohms in parallel with 70 ohms, the answer is 19.62 ohms. So again, the command window, or the shell, looks very much like MATLAB. In Python, you can have variables. To be a valid variable name, the first character has to be a letter. It can't be a number. Or it could be an underscore. The following characters can only be letters, underscores, or digits. So I could say like pi underscore value, that's okay. Other ones are not valid. This confuses it. It makes you think pi space value, that's two different variables, not allowed to do that. Dot has special meaning. This would be look for the variable pi under library value. Again, that's not really what you mean. It's got to be characters, letters, or underscores, digits. Python is case sensitive, just like MATLAB. So if I clear this out and say Jake equals 1, and then Jake equals 2, what is Jake plus Jake? The answer is 3. So with this, you can actually write code which is totally cryptic if you really want. Use random capitalizations. Please don't. A couple names you're not allowed to use, however. These have special meaning, such as while, return, raise. These are actually commands in Python, so don't make those variables. That's not legit. in terms of syntax. Syntax is very much like MATLAB. I have an equal sign. What it does is calculate everything on the right and assigns it to the variable on the left. So here it takes the number 123, assigns it to x. If I just do a number, the default is decimal. If I type in 0x, that means hex 123. I can assign 3 variables at once. I can assign variables in a matrix. It's actually the string, not really a matrix. I can assign the numbers 1 through 6. This is where it's a little bit different than MATLAB. It starts for 1, increments by 1, and stops when you equal 6. So it excludes the last one. This range of 1 to 6 actually gives the numbers 1 through 5. Whereas in MATLAB, you actually get the numbers 1 through 6. So a little bit of a difference. I can input a 2 by 2 matrix. Again, this syntax is a little bit different in Python than MATLAB. For a 2 by 2 matrix, here's the first row, 1, 2. Here's the second row, 3, 4. I can do operations in Python. There's add, subtract, multiply, divide. Slash slash is integer division. If I do something like that, trying to do Alt-Tab to get around. If I say, what is 7 over 3? The answer is 2.33. 7 slash slash 3. Okay, 7 slash slash 3. That's 2. That's integer division. 7 divided by 3, round down. There's modulus. In Python, star star is raised to the power. We normally say star star is convolution. In Python, it means power. So if I do like, what is 2 cubed? 2 cubed is 8. And if you have an array, I can add an element to the array with the command append. So if I have the numbers 1 through 5, I can add the number 6 to it. Kind of like this. Let's clear that out. Say x equals 1, 2, 3, 4, 5. So here's x. X dot append of 6. It's now 1 through 6. You can do logic operations. AND is logical AND, OR, exclusive OR, shift right, shift left. And this goes bit by bit. This is where you confuse everyone that's not an engineering major. I can sit there and say, what is 29, come again, what is 29 and 7? 29 and 7 is 5. You might be wondering what the heck happened. Well, this is binary 29. This is binary 7. Go bit by bit. If both bits are a 1, the answer is 1. If either bit is a 0, the answer is 0. So the only 2 bits that lined up were bits number 0 and bit number 2. Gives you 1, 0, 1, or 5. Shift left is a multiply command. So we say x equals 29. Y is x, shift left 1. Shift left is times 2. Shift right is divide by 2. If I say z is x, shift right by 1. Shift right is 14.5, lose the fraction 14. So that's kind of a way to multiply, divide by 2 is a shift command. Comments. In Python, this is a comment statement. And you can see the color is different. It's not going to execute that. There are conditionals. X greater than y, x less than y. I can say, is x greater than y? Nope, it's false. If I want to convert, this is a logic command. I can do what is the integer of x greater than y. Now it becomes 0, 1. I can round to the nearest integer. I can convert to a floating point number. Now Python is a little bit different than MATLAB. In MATLAB, well, Python's different than C, let's say. In C, you have to declare your variables before you use them because it's important. It needs to know, is your variable an integer, a character, a floating point number? In Python, you don't have to do that. It will figure out what the variable has to be on the fly. So, for example, in this program, trying to get over to Thonny. If I clear everything out, and say, what is x? Well, there is no x. I have to say x equals 3. I didn't have to declare x. It just says, create a new variable called x. It's equal to 3. X is an integer. If I say y is also an integer, 4, z is x over y. In C, what I would get is 3/4 as an integer. The answer is 0. In Python, it knows to convert this to a floating point number. If I want the answer to be an integer, I will use the integer command. Z is x / y. Now that's an integer divide. In Python, there's a print command. What print does is it sends the statement to the window, to the shell window. For example, if I say hello world, that shows up in the shell window. If I say x is 2 to the 5th power, print x, I get that. So this is something that's actually pretty nice in Python. Back under C in embedded systems, we had to work to send data to the serial port to get to the screen. I don't have to do that in Python. I can say print, spelled correctly, print hello, and it just sent the message hello to the shell window, something which is actually pretty hard to do in C with a PIC microcontroller. I can combine statements. I can say x is 2 to the 6th power, print that string along with x. They have x to the 6th is 64. You can prompt the user for input. So if I say something like x equals input, it's going to ask me to send this message, type in a number. I'll type in a number like 7. And now x is actually the string 7. When you input data, it's actually going to input a string. So if I do that again, this is actually perfectly fine. It interpreted that as a string, not a number. If I want to read that as a number, what I need to do is say, take the result, the string, convert to an integer. So prompt the user, read that as a string, convert that to an integer. So I say 83. X is now the integer 83. If I want to take a number like this one, it really hated it. I don't really hate that. If I want to get a floating point number, I have to use the command float. Now it reads a floating point number. That's a nice way to get input from the user. Again, much easier than what we did back in embedded systems. In embedded, we did that, but it was about week 7 or 8 until we could actually get numbers from the user. We can do that right away on lecture number 2. You can format the output to make it look pretty. If I use the format command, I can display the data in binary or in hex, in decimal, fixed point decimal, scientific notation, various things you can do. So with that, I can start solving problems. For example, if I had this circuit, find the resistance between A and B. Now recall from circuits 1, resistors in series add. In parallel, they add as the sum of the inverses inverted. So to solve this circuit, what I would do is have 200 in series with 300, gives you 500, in parallel with 450, in series with 75, in parallel with 250, in series with 50. Well, I can solve that in Python. So what I would do is first find these two in series, add them up, that's 500. Put these in parallel, so 1 over 500 plus 1 over 450 is 236.8. That's now in series with 75, in parallel with 250, in series with 50. So to do that in Python, what I would do is, let's just call this R1. R1 is 200 in series with 300. R2 is this combination. Take that result, 1 over R1 plus 1 over 450, take the inverse, call that R2. R3 adds 75. R4 will take that result in parallel with 250. So 1 over R3 plus 1 over 250, take the inverse, take that result at 50, and that's your total resistance, 188.75 ohms. So again, Python can be used just like a calculator, pretty much like MATLAB. So that's the command window. There's also the program window. Go over to Thonny. There's the window on the bottom. There's a top one up here that we've ignored so far. That's like the program window. That'd be like a MATLAB script. The stuff I type up here is executed when I hit the green arrow. So if I copy that, or type that in, come on, copy. Okay, so I need to create a new script up here. If I type in File, New, and paste, I can sit there and say, okay, let's input a value of R. R was that 300 ohm resistor we had before. If I hit this green arrow, that runs the script. So running it, it goes line by line. It first asks, what is R? If I type in 300, it then grinds through it, second line, third line, fourth line, calculates this is RAB. The beauty of scripts is I can now say, well, suppose instead of being 300 ohms, this was 250 ohms. 250 ohms. Now it's 186 ohms. 1, 2, 3, 4.567. 1, 2, 3, 4.567. Now 206.37. So that's what the top window does, the script window. I can sit there and execute my program. And that's what kind of these buttons do. I can open a file, save this, so I don't have to type it in all over again, run the program. Stop, what that does is clears out the memory, starts over. And this one is donate money to Ukraine, kind of a nice feature. So that's kind of the run icon. I can sit there and input different numbers. I don't have to sit there and type in the code over and over again, write a short little program. This is kind of like your programmable calculator. Input R, and it'll grind out what is RAB. Second example. Suppose I have this circuit. I want to find out what is the voltage V1, V2, and V3. Well, I can solve that using voltage division. V3 will just be what I'm measuring, 400 over the total, 400 plus 125. V2 is if I find the total resistance at this point looking right, call that R20. It's going to be what I'm measuring, R20 over 75 plus R20 times V1. V1 is this total resistance, R10, the resistance between 1 and ground for all this, over 50 plus that rate, plus R10 times V0. So if I know V0, I can find V1, find V2, find V3. To find R20, that is 300 in parallel with 400 plus 125. R10 is 200 plus 75 plus this mess. I can do that in Python. So first, given this circuit, I'll find out what is the resistance from node 2 to ground. That is 300 in parallel with 525. R10 is 200 in parallel with 75 plus R20, typo there. And then V1 is 200, well, this R10 over 50 plus R10 times 10. Once I find V1, find V2. R20 over 75 plus R20 times V1. V3 is 400 over 400 plus 125 times V2. I'll now print out the three voltages, and voila! I have solved the circuit using Python. I can do the same thing in the program window. I will let you input the value of R30. It will then calculate R20, R10, the voltages, and print out the results. So to illustrate that, I'm going to go over here, erase all this, paste it, and now run it. It's going to prompt me asking what is R30. If that was 400 ohms, it calculates R30, R20, R10 voltages, prints them out. These are the voltages if R0, R30 is 400 ohms. What is it if it's 700 ohms? I'll type in 700. Now these are the voltages. So that's kind of a program in Python. Neat thing about Python is it can handle complex numbers with no problem. Very much like MATLAB. So if I change the circuit slightly and make it this circuit, I've got capacitors which have a negative J term, inductors a plus J term. What is the impedance between A and B? Well, I can do that in the shell window. I want to put these in parallel. To input a complex number, I need to define what is J. So let's clear everything out. Clear all that out. And say J is the square root of minus 1. So minus 1 to the 0.5 power. That's J. If you're a math major, you call that I. We call it J. Just because for us, electrical engineers, I means current. Once I know J, I can say that Z3, going back to this figure, is J60 ohms in parallel with 40 minus J70. So Z3 is the inverse of 1 over J times 60. And it never hurts to use extra parentheses. If I don't do that, it actually executes left to right. It'll do 1 over J, take that answer, times 60. That puts the 60 in the numerator. If I add the parentheses, then it's J60, take the inverse. So it's that in parallel with the inverse of 40 minus J times 70. Parentheses. So J60 in parallel with 40 minus J70 is 69.2 plus J73.84. If you use a HP calculator, you can verify that's correct. Python works pretty well. It's pretty well debugged. Now add that to J30. Take that in parallel with 50. In series with 20. Add it all up, and I get the total impedance is 58.96 plus J 9.11. So again, Python will do complex numbers. I can put that in the program window. Same thing we did before. Define J, ask what is the impedance of C3, and I'll say it's going to be 70, meaning minus J70. Once I get that, I know Z3. I can find Z2, find Z1, find Z0, find the total impedance. If C3 is minus J70 ohms, the answer is 58 plus J9. If it's minus J45.678 ohms, the answer is 54.26 plus J7.45. Finally, I can do voltage division with complex numbers. Again, suppose I have this circuit, find V1, V2, V3. The procedure is the same as before, except now I'm using complex numbers. The first thing I need to do is represent these as impedances. So if you recall back from circuits 1, a resistor is just R, inductor becomes J omega L, C becomes 1 over j omega c, and voltages become A minus JB, where A is the cosine term, B is the sine term. So if I do that, this becomes 8 plus J0, 8 cosine, 0 sine. This is 20, that's 50. This becomes J omega C, correction, J omega L. Omega is 100. So 0.1 times 100 is 10. This becomes J10. 1 over J omega C, that's 100. And I can sit there and say, what is, omega is 100. What is 1 over J times omega times C? No, that's J omega L. What is J times omega times L? L is 0.2. That becomes 0 plus J20. I knew that. And this one, the capacitor becomes 1 over J times omega times C. C is 0.01. Becomes 0 minus J. So what I would do is input omega, find this impedance, C30 is 1 over J omega C, C20 is J omega L, Z 1, 2, impedance between nodes 1 and 2, that's the notation I'm using, J omega L. Z3 then, impedance from 3 to ground is minus C30, C2 is this impedance in parallel with that one. C1 is 50 ohms in parallel with that mess. That mess is C12 plus Z2. V0 is A plus J0. V1 is then by voltage division R1 over R1 plus R2. That over the 50 over 50 plus 20 times V0. Well, C1. Find V2 by voltage division, find V3 by voltage division, print out the voltages. So this is if I just did that in the shell window. I can find the voltages in terms of complex numbers. Again, what that means, real part's cosine, minus J is sine. So this one actually means it's 4.65 cosine of 100t minus 2.218 sine of 100t. And that's phasor analysis. I can put that in the program window. I'll ask the value of C in farads. It will then calculate the impedances, grind through everything else, print out the answers. If C is 0.01 farad, these are the voltages. If I change C, I can find the answer for different values of C. Now there are differences between MATLAB and MicroPython. MATLAB is matrix language. MicroPython is not. Again, MATLAB was designed for engineers and scientists. Engineers and scientists use matrices very extensively, so it's important that they have a language that handles matrices well. Python is written for the general public. Not everybody uses matrices. Actually, very few people know what a matrix is or how to use it. So Python does not really handle matrices the way you would expect. For example, in MATLAB, if I say A is the matrix 1, 2, 3, 4, B is 2 times A, I take each element and double it. If I say C is A times A, I get the matrix squared. That's MATLAB. MATLAB is a matrix language. In Python, however, if I say A is hello, B is 2 times A, it takes the string of A and copies it. If I say A is the matrix 1, 2, B is 2 times A, I get 1, 2, 1, 2. If I say, what is A times A? It says, you cannot multiply strings. That's nonsense. So again, in Python, this is actually a string. It's not a matrix. You can fake it. You can create it, write subroutines so it looks like a matrix. And we'll actually be doing that later. Just realize that Python and MATLAB are a little bit different. Python does not handle matrices. So that's kind of the idea of Python and Thonny. So Thonny is very, very similar to MATLAB. It's got a shell window and a command window. That looks like the command window and the program window in MATLAB, or the script window. You can type programs or type commands into the shell window, and it'll execute them one by one. You can put commands into the program window and run them, very much like MATLAB. So again, if you're familiar with MATLAB, you're kind of familiar with Thonny. So that's kind of lecture number 2. What we're going to look at next is doing looping. How to do loops, while loops, for loops, and if statements in Python. But that'll come up next. So that's lecture number 2 for ECE476.